Okay, hello everyone. In the previous lectures, we mainly learned about white box testing method, including dynamic symbolic execution and gradient-based deep neural network testings. So in this lecture, we will learn about the gray box testing method, which contains the characteristics of the both white box and black box testings. And in my personal opinion, the gray box testing method seems to be more effective in the bug finding than the white box testing in the both academia and industry. So the gray box testing method is still being actively researched mainly in the security field. Okay, let's start with these lectures, this week lectures. Today, I will introduce a well-known software testing method, gray box testing. And this technique is usually called gray box fudging or just fudging. And there are two major approaches for fudging, which are mutation-based fudging and the generation-based fudging. Today, we will focus on mutation-based fudging techniques. And in particular, we will learn how AFL, which is one of the most famous mutation-based fudgers, works. Okay, let's start. Before introducing what gray box testing is, let's start from the difference between black box and white box testings. As I mentioned in the previous lectures, the key difference is that black box method performs testing without observing the source code, while white box testing do testing with carefully observing the source code. So that is, black box is usually very fast but naive because it just takes a binary file as input and randomly generate many test cases. And conversely, white box testing such as symbolic execution is relatively slow but systematic, as it generates the test cases by observing the path condition constraint like this. So what is the gray box testing? At a high level, we can say that this technique contains the characteristics of both white box testing and the black box testing. And in my opinion, gray box testing is more like black box testing than white box testing. Anyway, as it includes both characteristics, so gray box testing is usually more faster than white box testing method and is also more systematic than black box testing method. And as you can see, a gray box testing can take either a binary file or source code. So the difference between gray box and white box methods may seem a little bit unclear. In fact, this distinction is sometimes unclear actually. Anyway, let's clarify the key difference between gray box and the white box testings. The key difference is whether this technique is to use the source code partially or fully. That is, gray box testing method obtained only partial information such as code coverage like branch coverage or statement coverage or bug finding result from each program execution with a given test cases. For example, as you can see from the picture on the left, when executing the program with a given input, gray box testing only obtains the number of covered branches, and that's it. On the contrary, when executing the same program, white box testing such as symbolic execution, as you know, will update concrete and symbolic state and path condition and generate the test case by resolving the path constraint. So in short, gray box testing used only partial information from the test execution. But it is faster than the white box testing. So in general, gray box testing or fudging technique is classified into two different styles, namely mutation-based fudging and generation-based fudging. And the difference between the two techniques lies in how to generate the test case. First, mutation-based fudger takes valid seed inputs such as XML file or MP3 file or PDF file and so on, and generate the test case by slightly changing these valid seed inputs. And the second generation based fudger takes a grammar as an input, not a valid seed input, and generate test cases with this using grammar. For example, mutation-based fudger takes as input 1 byte seed and generate a new input by flipping the first bit of the original inputs. So the key decision making in mutation-based fudger is where to mutate and how to mutate. This is key in mutation-based fudgers. On the other hand, the generation-based fudging takes the predefined grammar as an input and generate the new input through the derivation of the grammar. So for example, it generates new input BDD. So it's starting from S in the grammar, and it first derivates the character A and C, and then the character A will derive and B and C, and finally C is determined as D among the D or E according to this predefined grammar. So the key component of the generation-based fudger is how to generate the grammar effectively and how to derivate from these grammars. So in these lectures, we will focus on the first fudging techniques, mutation-based fudging. So the intuition or the hypothesis in this technique is that mutating only a fraction of a valid seed may generate good inputs in terms of fog finding or code coverages. For example, suppose that we aim to generate the test case for the target program taking like well-structured file such as MP3 file as an input. And as you can see in the bottom figure, the valid format of MP3 file is quite complicated. So if we generate test case from scratch without valid seed input, it is extremely unlikely to generate useful test cases. That is, the generated input by pure random testing from scratch will most likely cause just parsing errors, so which is failed to test the core functionality of the target programs. So mutation-based fudging basically assumes that it takes highly well-structured CD input like PDF or XML as input and changes them slightly. That is the basic assumption of the mutation-based fudgers. Okay, let's see the rough workflow of the mutation-based fudging at a high level. So it first takes a set of valid seed inputs and the target program under test. And the first step, which is the seed selection, is to select a seed from the set. So then the second step is seed mutations, is to generate the input by slightly changing this selected original seed. Usually, these mutated inputs are called mutant. So until time testing budget is over, the mutation-based fudger repeat this process, selecting seed and selecting and mutating seed, and then return the generated mutant and found bugs as outputs. So as you can see, its workflow is quite simple. And as you might already know, AAFL, which is American Fudge Loop, is the most famous open source mutation-based fudger. And numerous fudging techniques have been implemented on top of AFL. Even today, the interesting ideas of many researchers are constantly being applied to this tool AFL. And as you can see, this captured figure is taken from the URL below, and it shows how many other fudging techniques are associated with AFL. So if you are interested, go to the URL below and take a look. And as you can see, you will find that there are so many fudging techniques out there. So we will learn how this representative fudger AFL works in these lectures. So the input of AFL, a seed pool which consists of valid seed inputs and the target programs. And at first, it selects a seed from the pool based on its own selection criteria. Second, it mutates the selected seed through the determining stage, and namely havoc stages, and returns the namely interesting mutant among the total generated mutant. And I will explain later what the interesting mutant is. And okay, then it simply adds this interesting mutant into the seed pool, and then repeat this process until the testing budget expires. And as you can see in this workflow, the key ingredient of AFL is seed selection and seed mutations. So let me introduce each component one by one. So the first, the seed selection of AFL is simply done selecting a seed from the queue sequentially. So it first loads this initial set of seed input into a queue. And suppose that the 5 seed inputs are given, and it loads 5 input into a queue and simply select the first seed in the queue. Then the seed mutation step takes this selected seed S1 in this case and mutate the seed S1 based on its own mutation strategies, and returns the mutant such as from M1 to M10. And then AFL checks whether each mutant is interesting or not, and returns only interesting mutants such as M2 and M7 in this case. So more specifically, AFL has 2 criteria for interesting input. First, if the input causes a program crash at the target program under test, AFL considers this input is interesting. Second, if the input is able to cover a new execution path which has not been covered so far, the input is also the interesting input in AFL. So based on these criteria, AFL adds this interesting mutant such as M2 and M7 into the seed queues, and select the next seed input as 2 from the queue. And when reaching the last seed in the queue, and it select the last seed and go back to the first seed of the queue again. So that is, as you can see, there is no specialized seed selection strategy in AFL. It just chooses each seed in order. Okay, let's talk about the next step, seed mutations, where the job is to determine how to mutate a given seed.